Hello everyone and welcome to this webinar, the latest in our webinar series. We're delighted to see so many present today from the west coast of the United States, through Europe, through Asia and out to Australia and New Zealand. Thank you very much for your time, and we hope you get a lot out of this event. I'd like to introduce our team today. My name is Philip Ike. I'm the Marketing Communications and a Regional Manager at LUSAS, and my colleagues.
I'm Steve Rhodes, I'm a Chartered Civil Engineer.
I'm Paul Belchamber, I provide general marketing and sales support to these guys.
During the webinar, we encourage your interaction. Please do interact with us. You can ask questions through the GoToWebinar Questions panel, which you'll see in the dialogue. You can also send emails to us at any time on webinars@lusas.com. Depending on the traffic, we'll get back to you on these comments during the event. With those that we can't, we will come back to you shortly afterwards. This presentation is being done with LUSAS version 15.2, which has been recently released and is available in the user area of our LUSAS website. It incorporates some change to traffic loading codes. Some of these are particularly relevant to the presentation we're doing today, as they are assessment-based codes. So we have inclusions of the UK assessment codes, BD21, 8634, an update to Australian and American assessment codes of practice. Alongside that, the traffic load optimizer is always being updated and has been improved and further optimized with this release. This webinar is on the subject of rail bridge assessment using LUSAS software, and it is based on the Network Rail Guidance Note, CIV 25. I'd like to hand you over now to my colleague Steve Rhodes, and he will take you through the technical presentation.
Thank you, Philip. So today we're exploring ways to mitigate assessment failures by improved modelling. We'll focus on U-frame bridges because that's a common bridge type in our rail network, and analysis approaches which would come under a level 2 assessment in the Network Rail Guidance Note. So we'll be looking at how we can use elastic or eigen buckling analysis together with codes of practice rules to obtain a less conservative moment of resistance. And we'll look at how nonlinear analysis can help us further. We'll also discuss several issues along the way, such as idealization, interpreting the results, and initial imperfections. I'll be building an example U-frame model in LUSAS, showing you where to find the key functions of interest. Now, the Steel Construction Institute publication 318 is a great resource where you can read about U-frame design concepts, but the primary issue we're looking at today is the potential buckling of the main girders. So the top flanges are in compression and are susceptible to lateral instability. They can buckle outwards or inwards, and they aren't restrained by bracing at the top flange level as you'd expect in many other designs. Instead, they're restrained to a greater or lesser degree by the so-called U-frame action. So this is the strength of the main girders in buckling. It's dependent upon the stiffness of this U-frame. It's formed from the web and the web stiffeners and the cross members. The cross members are usually standard UC sections, steel-eye sections that is, and they are in turn stabilized by the deck, which might be a reinforced concrete slab as illustrated here in a modern bridge, or it might be formed from a stiffened floor plate. Or in older structures, there might be jack arches, precast panels, buckle plates, troughs, all sorts of construction have been used. In some cases, we might choose to include the deck in the analysis where it forms a diaphragm, and this could be very beneficial to the stability of the main girders. In other cases, we might conservatively ignore the contribution of the deck to both the stiffness and the strength in tension in that lower part of the deck. Our example today is a U-frame bridge of span 42 foot, just over 42 foot, 13 meters. The girders are 2'4" deep, and they're placed 10 foot apart with universal column sections between them. Connections vary from bridge to bridge, but in this example, we will assume that the cross girders are fixed to the web panels rather than the web stiffeners. This makes the system rather more flexible. The flanges of the main girders are plated. They total 2.5 inch thick in the central section. That's the yellow flanges in this illustration. So the section there is quite chunky. In our example, we will ignore any contribution of stiffness from the deck, but we will of course include its weight. And working to the Network Rail Guidance Note, Civ 25, we find that Section 5 essentially refers us to the methods of BS 5400 Part 3, with some additions and amendments. And carrying out manual calculations on that basis, we find the design resistance, MD there, of each main girder to be 1,892 kilonewton meters. If we use the elastic buckling method, which I'll show you shortly, which is still using the provisions of BS 500 Part 3, we can obtain an improved value. In fact, a 41% improvement upon the manual method. And if we carry out a full nonlinear analysis for this example, we obtain an additional 70% if we take the manual method as our baseline, which gives us a significant improvement in route availability according to table 4.3 of the Network Rail Guidance Note. Obviously, with different examples, the improvement may be more or less significant. So, how do we set about modelling a U-frame bridge in such a way that we might reap those kinds of rewards at the end of the process? Well, our recommendations would be to start out using shell or surface elements rather than beams. Although beam elements are very efficient and can be used in a number of ways for this sort of analysis, using shell elements will ensure that both local and global buckling modes are identified and can indeed contribute together to the predicted failure of the member in a full nonlinear analysis. And using then shell elements, we should carry out a linear static analysis and check the model before proceeding any further. Next, run an eigenvalue buckling analysis. If you're going to go on to a full nonlinear analysis, this helps to bound the problem, and by using the results together with the code of practice, BS 5400 Part 3 in this case, you can, as we've already seen, achieve what might be a quite significant improvement in predicted capacity. And then with the eigenvalue buckling behind us, we can build up to a full nonlinear analysis. So more on that a little bit later. Let's first then take a look at how we could construct our example U-frame bridge entirely using surface elements, shell elements, and then we'll return to our considerations of buckling. Our U-frame bridge, this example is an old structure, and so the drawings are in feet and inches. It may be convenient to work in those units to begin with, and then to change units and scale the model later in the process, since UK and European codes are written in metric units. And remember, we will be modelling using entirely surface elements, shell elements. So we want to create some surfaces to represent the plates in this model. But we can start just by drawing some lines. And these two lines represent the bottom edge of a bearing stiffener or an end plate. I sweep these lines 8 inches in the Y direction. And when I sweep a line, I get a surface. It's a bit like extrude in AutoCAD. And I sweep these lines another, say, 1'8" in the Y direction. So I have now 4 surfaces which together represent a web stiffener, which is 2'4" overall. I divided the stiffener in the middle, as this is where the web connects. And these, if you like, are the flanges of the main girder. If I sweep these lines in the Z direction, you can see I've now got an end plate and a short section of eye girder. And if I copy this, I've now got sort of a small web panel and a part of the next panel. I'm going to create some more of that panel. I'm going to do it in a special way in order to make it easy to connect the cross frames. So I sweep these lines again, 4 inches, and again. I need to sweep it in the right direction. And then one more time. Okay. And I've created sort of half a panel, and within it you can see there's a kind of very small eye girder there. That's the end, if you like, of the cross girder. Just selected there for you. So if I sweep those lines in the X direction, 10 foot, then that will create a 10-foot long cross girder. Just rotate around. You can see that I've got half a panel and a cross girder. Now if I copy that, Z direction, 2'8". And again, that's now a full girder with 2 cross members, full web panel. And again, if I copy it now in the Z direction, 5'4". I've got 1 panel, now I want another 7 panels, that gives me 8 panels in total. And I've got 8 panels and 16 cross girders. Now I'm just going to select the web stiffener and end plate. And if I copy that to the other end of the girder, just over 43 foot away, I've now got, that's about 13 meters, as I say, that's 1 full girder and all my cross members created. If I look end on the bridge, that's my girder here, there's my cross member, and I can copy that girder over in the X direction, 10 foot. Now that completes the geometry of this model. Just rotate around, maybe if I just make it solid so you can see a little bit more clearly what I've created. Okay. Now perhaps at this point I decide to move over to SI units. So I would go to the model properties and choose some kilonewtons and meters, say. When I choose that, you'll notice LUSAS gives you a message which says that it's not actually going to scale the model, because of course I might be changing the units because of an error and not want to scale everything. But it's very easy to scale. So if I select the model and move using a scale, I can then convert from meters to feet. And you can see I can enter scale factors that are different in different directions if that's useful. It sometimes is useful, but in this case, of course, I'm scaling everything down from feet to meters. And you can see now my girder is around about 13 meters long. Now I need to give a little bit more information about that model. I need to add attributes to it. So I go to the attributes menu, and first on the list is mesh. And this is where I can tell LUSAS that the surfaces in this model should behave as, mathematically, if you like, as thick shell elements. And I can also set here an element size. And if I assign that thick shell mesh to my model, I've assigned it to the whole model, so I selected the whole model, which is applicable, and I drag and drop that attribute across. Maybe if I just show the mesh on top, you'll be able to see those grey elements showing that my model is now meshed with thick shell elements. But if I want to change the element size, if I change my mind about that at any point, and it could be today, next week, whenever I change it, I can always just go in here and switch the element size, and that's a very simple way of being, it gives me the ability really to check the mesh refinement at any point I may need to do that. So you can see the mesh is updated there. Now I need to put in some plate sizes. So I go to the attributes menu and choose geometric and surface. And I can enter a surface thickness here. This is now working in units of meters, of course. So if I wish to put in a half-inch plate, I can choose the unit conversion here. And you can see LUSAS will convert it for me. That could be my web stiffener. and I press apply. When I press apply, you'll see that I get that attribute appears over in the attributes tree view. It's grey because it's not yet assigned, but so it's just like pressing OK, but it retains this dialog for me to enter another number. So I can then put in maybe a 1.5 inch plate for my, say my flanges at the ends there. And I'll OK that now. Now I obviously have other plate sizes to enter, but to save a little bit of time, I can actually import those. If I go to import, export model data, you can build up your own library. When you create, as I've got here, the web stiffeners and flanges that are in my model, I can export them into a library, and then of course I can bring them back from that library in other models. So I've already got some items which I've created in other models which I can bring into this model now. So I'm going to import from the library to the model some geometric properties. I'll also import a few utilities which I'll speak about in a moment. So when I OK that, you'll see I've now got a range of plate sizes here, and I've also imported some favourite views. You can save a view at any point during creating a model, and as you can see, you can also export that view and import it just like anything else in your model. So if I apply this home view, this is showing me the model end on, and it will colour in the different geometric thicknesses as I assign them. So I'm selecting these two girders, and I'm going to assign the web stiffener thickness first of all to everything. And you can see then everything's gone red. There's two girders. Now I'm going to select the flanges, just assign the flange thickness 1.5 inches to those. I also have the web stiffeners. That's a thickness which I actually imported just a moment ago. And I can select those and add them. And if I just rotate the model around a little, you can see there I've got flanges and web stiffeners looking good. If I now look down the X direction, I can pick the area of those flanges which is thickened, which has doubler plates up to 2.5 inches along those sections. If I just drag that across, you'll see when I rotate around. Now I've accidentally assigned that to some of the cross girders, so I can just select those. It's the next job anyway. And when I select all of those correctly, holding down the Alt key there, I will be able to assign the cross girder thicknesses there as well. So you can see now I've completed the thicknesses as well. Moving on down the attributes menu, I just need a material. I can choose this time from the material library. And for this, because it's a rail bridge in the UK, I'd use Steel UK and Network Rail. That fills in all these properties for me. When I OK that, it appears as an attribute on the tree view. I can then assign that, in this case, to all of the items in my model. Again, working my way down the attributes menu to the supports, I would choose to have sliding support maybe. Let's put this as a sliding bearing. When I OK that, again, the attribute appears over here. Now, obviously, I would need fixed bearing, pin bearing, various different support conditions might be appropriate for your model or for this model. I'm going to import some more support and indeed some loading attributes. When I OK those, see I've got several supports there. All these are, as you can see, are just fixities. What I'd need to do then is, of course, assign them in my model. So I'm currently just looking at the thicknesses at the moment. Maybe it's a little bit more useful at this point to see just a part of the model like this. I can zoom in, and if I assign my sliding supports to that line, so that's underneath the bearing stiffener, and then I assign a pin support to that point, that's pinning the bearing at one end of my structure. Now, in certain circumstances, you may have bearings which do not rotate, sort of knuckle joints or something, so you may not wish to have rotation, and it's pretty important to get those support conditions right, particularly for U-framed bridges. I'm putting a guided bearing at the other end there. If you don't get those supports correct, then obviously you'll allow torsion at the ends of the girder, which may not be possible in real life, and that will significantly reduce the capacity of your girders in the calculation later. So finally, I just add the support of this last corner. And I have got several loads here, but to save a little bit of time, I should just add the dead load here. I'll just add gravity, so the self-weight of the structure in locus number 1. And now I've incorporated everything that I need in my analysis model, my linear static analysis model. So first of all, I would always recommend that you solve a linear static model, a linear elastic model, rather than going straight into a buckling analysis. Always solve it. It gives you a chance to carry out a few checks and just look at some of your results and decide whether you think they're reasonable. In the interests of speed, I won't go on and create all of those other low cases perhaps and carry out the checks that you would normally do. I'll just, well, if I just jump to a model which is essentially similar to this, you can see the results. In fact, the stress is there, even a little jump in stress where the flange plate changes size. So that's working nicely. So here's a very similar model. It just includes 4 low cases. So we're going to omit the checks that I would usually carry out at this point, and instead we're just going to move straight on to creating that eigenvalue buckling analysis. That's very simple. First, we can make a copy of our linear elastic analysis. I'm doing that by holding the control key and dragging, just like you would when you copy a file in Windows Explorer. I'm going to call that analysis 2, eigen buckling. Now, I want to put all my loads into locus number 1, because obviously this structure will buckle under the action of combined loading, not just one set of loading. So I'm going to combine all those loads into locus 1. I'm doing that just by dragging and dropping, just like when you move files around in Windows Explorer. And I can delete those empty locases. Just rename that total load. So that locus now includes all the loads. And indeed, I can see them listed inside here. So finally, to get my eigenvalue buckling analysis running, all I need to do is to switch on the eigenvalue controls. Right-click there, choose Controls and Eigenvalue, and choose a buckling analysis, a buckling load. Now we can request any number of buckling modes up to the number of degrees of freedom in the structure, which is probably too many, but it's usually the lowest modes which are of interest, the modes where the structure buckles at the minimum load. So I usually recommend 5 or 10 modes, and I like to look at those various mode shapes as they may indicate something about my model which just isn't quite right. But that's it. Essentially, the buckling analysis is ready to solve. So I'll just solve that. Sure, while that runs, I wonder if there's any questions coming through that we could talk about?
Hi, Steve. Yes. Whilst that's running, we will just answer, there are some questions that have come in. One that's been asked a few times is, whilst building up the model here, we've been using LUSAS from scratch. The idea behind this is to show you how the modelling environment works in its entirety. You could also use CAD to import. So a few of you have been asking what the import functionality is. The standard formats, or the well-recognised formats that we support, are DXF, STEP and IGs. We also, in the pre-release of the next to be released, version 16 of LUSAS, now have a functioning BIM import facility as well. So depending on what kind of data you have, how good that data is, yes, CAD is obviously a very valid way of getting modelling information into LUSAS. The other question that we've had just a couple of times, sorry Steve, is the deck in this case has not been modelled. And as a few people have pointed out, could it be modelled? Well, yes, these are shells that Steve is using here. And the deck, Steve, could also be modelled as a shell and could be connected to the existing substructure in a variety of ways. So yes, it's certainly possible.
Absolutely, yeah.
Okay,
We've included it only as the dead load here, so we might wish to, as I mentioned earlier, include it as a stiffness.
Absolutely. Okay. Well, look, Steve, I'll let you carry on.
Thanks. So as you can see, that's obviously solved, and we're looking now at the buckled shape of the girders. We're looking at the lowest mode, the first eigen mode, the first eigenvalue number 1. We see that buckled shape. And along with that, we see an eigenvalue load factor in this example of 14.7. With mesh refinement, that value will actually come down a little. Alternatively, if we use quadratic order elements, I use linear order elements there, if we use quadratic order elements, we get a more accurate load factor with the same number of elements. So this is where we see a load factor from that eigenvalue buckling analysis of 11.5 for this global mode. But the question is, what does that really mean? If the applied moment is 1,287 kilonewton meters, does this mean that our girder is safe up to about 14,800 kilonewton meters? Absolutely not. It does not mean that. The eigenvalue load factor we've got is unconservative, just like Euler buckling. So eigenvalue, buckling, elastic critical loads, Euler buckling, these are all based on assumptions of no plasticity, no imperfections, no load following. And so eigenvalue factors like buckling loads are generally unconservative, they're upper bound, they're unsafe. There are a few exceptions. There are some special cases where web panels with edge restraints and the panels can carry loads through a tension field effect. That gives them some significant post-buckling reserve. But in the general case, and in our case, the real failure load is lower than the elastic buckling moment, the elastic buckling load. But in accordance with the network rail guidance, we can use BS 5400 Part 3 clause 975, which uses that elastic critical moment, MCR, to define a slenderness for lateral torsional buckling, lambda LT. In this case, we find the lambda LT to be about 51. And then we can use figure 11. With the slenderness entered on the x-axis, we can find the moment of resistance as a proportion of the ultimate moment. In this case, 80% of the ultimate moment, which is the plastic moment because the section is compact. And the design resistance, MD, is obtained from MR just by dividing by the partial factors for material and load effect, F3. This is very similar in approach to the Eurocode. In this instance, this eigenvalue and codified method gives us 41% greater capacity compared to the manual method of BS 500 Part 3 and increases the route availability quite significantly as well. But as good engineers, we should ask ourselves, is this for real? You know, is there something in the code which is missed by the model? Are the results sensitive to something in particular? We should always have that healthy skepticism. Now, it's helpful to run test models such as a girder alone or a girder with fixed supports at each U-frame location, that sort of thing that bounds the problem. But thinking about where the differences might arise also gives us some hints concerning sort of special modelling considerations which are relevant to these bridges. So first, I've already mentioned, we really must check the support conditions used in that FE model. In that example, I allowed plan rotations at the bearings, while some bearing types would restrain plan rotation. And in those cases, the calculated moment of resistance would be significantly greater by restraining them. In the manual calculations, the rotational stiffness at the ends of the compression flange can be incorporated by using BS 500 Part 3 Figure 7. But it's very difficult to assess that correctly without using a model like the one we've built today. So maybe now we have that model, we can go back and improve that manual calculation. Second, our FE model includes variable flange sizes, which of course the code doesn't, and it could have included corrosion, even local corrosion or damage. That's going to have an effect on the calculated moment of resistance, which isn't easily incorporated into the manual calculations. Thirdly, the connection between the cross members and the main girders. In our example, the manual calculations to clause 96413 showed that the connection itself was effectively rigid by comparison to other parts of the U-frame. So we could know in advance that the flexibility of the connection could be neglected in our model. If the connection is not rigid, that approach would result in an overestimate of the buckling load. So the flexibility should then be included in the model using joint elements. And you could get a stiffness for those joint elements from the network rail guidance note, where figure A46 gives the values of flexibility for a range of different connection types. Our eigenvalue analysis also did not include material plasticity, imperfections, or residual stresses. However, we used the results to find a slenderness, which we then interpreted using BS500 part 3 figure 11. In that way, we have actually incorporated those issues in our calculations, so no problem. But there are some issues which are not handled either by the eigenvalue analysis or by the manual calculation, namely liftoff, connections which have some wobble to take up before becoming effective, the effect of local buckling modes which might exacerbate a global failure mode, post-buckling strength of web panels due to tension field effects, all these sorts of things. So as an alternative to eigenvalue and code calculations, we can create a nonlinear model which takes into account large displacement theory along with all of these issues, even joints if necessary. And the good news is that the model we've already constructed is very close to the kind of model we would need for a full nonlinear analysis. What we would need to do is include initial imperfections. It's based on a measured bow in the top flange, then that should correspond to about 1.2 times the measured out of straightness for the compression flange. That allows for the unknown residual stresses in the girder, those that were locked in during fabrication. The shape of the imperfection can be conveniently based on the buckling mode shape, which is already identified in our eigenvalue analysis. That's only a click away. And indeed, it is actually the suggested method in the Eurocode. We also need to turn on geometric nonlinearity. That instructs the software that we're going to use large displacement theory. And we need to ultimately include material nonlinearity as well. Let's see where those settings can be found in LUSAS. So let's start by creating a nonlinear analysis. It won't include plasticity, but let's just create that. Let's copy analysis number 1. I'm holding control and dragging, and I've now got analysis number 3, which I'm going to call my nonlinear analysis. And we can delete the eigenvalue control and switch on a nonlinear control instead. If we use an automatic incrementation, then the load factor will ramp up. And here for simplicity, I'm using a single load case with the total loads applied, which is comparable to the eigenvalue analysis. In a real project, we might use several load cases, keeping the dead loads steady and ramping up the live loads on the top. But with this automatic incrementation, we can ramp up the load factor up to, well, we know that this model should fail at something less than 14.7 or 11.5 if we use that more refined model. So if I put in a maximum load factor of 20, if the analysis converges right up to a factor of 20, then something's gone wrong. It should fail before that. The starting load factor obviously needs to be something less than 14.7. So I'd suggest 5 or 10% of the expected load. That might be a good starting point. So here I'll use a starting load factor of 1. And that controls the loads, but we need to tell the software that this is a geometrically nonlinear analysis. And we do that in this nonlinear analysis options box. We just switch on under geometric nonlinearity, total Lagrangian option. That's appropriate for thick shell elements. If you're using other element types, check the help file. Lastly, we need to include an imperfection. Now, by double-clicking on the analysis here, I can access this option for initial deformations. It defaults to starting with an undeformed mesh. In this case, we choose start with a deformed mesh from analysis 2. And I'm going to take mode number 1, which is the one we're looking at the moment. Now there's a scale factor. Now an eigenvalue buckling analysis is always normalized to a maximum displacement over here of 1 in whatever units we're working in. Now in this case that's 1 meter. Now that's probably a bit big for an initial bow. In a modern structure we'd expect that to be maybe a bow of span upon 300. That's from the Eurocode. If this is an old structure, we could maybe use twice that. So let's say span upon 150. So that would be, in this case, 13 divided by 150. Anytime you type in a numerical box an expression, LUSAS will evaluate that for you. And that's it. I'm basically ready to go. But of course, I would want to ultimately also include material plasticity. And I would do that if I just edit this attribute here I can make it into a plastic material, and I can enter a yield stress, something like 235 megapascals or something like that. I can assign that material into analysis 3 or into a new analysis 4, then I can build up the nonlinear behavior a step at a time. Ideally, I'd use a hardening curve, but I'll refrain from going on in that direction now. If you were using a modern bridge, standard hardening curves could be used, although we should always take care to make a conservative assessment of the hardening. For older bridges, material properties must be considered really carefully. A level 2 assessment might make use of test results to identify material, and then the network rail guidance note requires the use of table A2 for those yield strengths and tensile strengths. This animation shows the geometrically nonlinear analysis. That is, imperfections are included, large displacements are calculated, but plasticity isn't included. And we can see the load being ramped up, and the final buckled shape there is very similar to what we saw in the eigenvalue buckling analysis. This graph from the same analysis shows how the lateral displacement in the top flange at midspan tends to increase without limit as the load factor reaches near to 11. So this is a very similar story to our eigenvalue analysis, but this reflects the level of imperfection. The larger the initial out of straightness, the lower the load factor at failure. This graph also shows how pre-buckling deformations may be significant. Long before the elastic or eigenvalue load is reached, the lateral displacements may become significant, and that would give you eccentricity in the loading regime and would give you perhaps some serviceability limit state concerns. This, on the other hand, is a full nonlinear analysis. That includes the imperfections, the large displacement theory, and the material yielding. So this model is capable of capturing the true behavior of the bridge. That would be contribution of local modes and global modes in the failure, any interaction between stresses in the flanges and the web stiffeners, post-buckling reserve, tension field in the web panels, and so on. Those black dots show where the yield is being reached. If liftoff were required, that could also be included, and likewise for slack connections, which could be added as joints if necessary. And this graph shows how the failure load comes at around about 2.8. Clearly that's very dependent on the material properties as well as the imperfections. So the design resistance there comes from the failure load factor. Some engineers prefer to use the load factor at first yield, but either way, the partial factors gamma M and gamma F3 need to be applied. And finally, just recap those stages. First, we started with a linear elastic analysis suggesting shell elements for local and global modes. We carried out an eigenvalue analysis. We looked at the buckled shape. We checked the behavior, and we checked using the code rules there, clause 975 for a member resistance. And then optionally, you can go on to nonlinear analysis, testing it probably first using a geometric nonlinear analysis and large displacements, and including the imperfections there. And lastly, adding in material plasticity. Okay, well, before we close, you might want to make a note of some of the references used in this presentation. In fact, this webinar has been recorded, so you can watch parts again and indeed come back to this slide for the references there. So with that, we're running short of time. Perhaps I should hand back to you, Philip.
Thank you, Steve, and I trust that's been a very useful summary for you of steel bridge assessment in LUSAS. More details on this, on rail bridge assessments, and indeed many other subjects within bridge analysis are available on our website. You can contact us directly through email. So for those of you that don't have direct contact with us yet, use the info@lusas.com. For those of you that we already have a relationship with, please just contact your account manager directly, and you have our four faces at the foot of the page here. Just to follow up on some other items, video content is being extended with LUSAS presently. The webinar that you've seen today, Steve has already mentioned, will be made available after this presentation. It's made available on our website. We have also, though, recently launched a YouTube channel, and the webinars as well as other presentational videos go up onto that YouTube channel. We would encourage you to subscribe, share and like, and generally interact through YouTube, and we very much value any comments on that service. For next webinars, we're keen to know what you would like to see from us next. We will be sending out some survey information in the next weeks and requesting information from you on content. So soul structure interaction is a subject that we've had in mind and has been much requested. For more advanced users, the area of software customization, parametric modeling is of great interest. We, I think I mentioned earlier on, have a version 16 which is currently in development. That version 16, there will also be a launch webinar associated with that. Don't forget as well that if you want more assistance in using LUSAS in the way that Steve has demonstrated today, obviously he's a trained expert, and we'd like to get you all up to this kind of level. We offer support on different levels and in different ways. We have traditional hotline support, so talking to a human being, which we hope you value. Other areas of technical support, we have a LUSAS user area. So on this is a knowledge database that you can interact with and ask questions and gain answers and source articles. Training courses are scheduled regularly in our head office and also in regional locations. And we can also offer bespoke training courses to certain subject matter in your offices. And we get glowing reports on the training courses and on our technical support, as you can see on this page. So we put a lot of effort into the quality of the support that we offer you, and we would encourage you to take best advantage of it. Something that many of you may not be so aware of, LUSAS is recognized strongly, obviously, as a piece of software. We are also consulting engineers. In fact, we've been running as a consultancy team for some 20 years or so and have a very strong experience across a broad range of structural types. So whether you're looking to employ a consultant to transfer knowledge, in other words, in a sort of training facility, whether you just need extra manpower and secondment of staff, assistance in manipulating the software to particular functions with customization, or to act as a third-party design or checker, we can offer this kind of facility for you in-house. And again, we've had a lot of experience in this, and we get very strong commendations from our users, as you can see here from URS in the UK, for the assistance we gave them on the very beautiful cable car in London that you can see on the screen. Questions? Again, we'd encourage you, please interact. We have had a huge amount of questions actually since the last question session. I think some of those, or many of them actually, have probably been answered by Steve in the second session, because we noted a lot coming through to do with nonlinearity and to do with things like initial imperfections. Many of those hopefully have been covered. We will get back to the others of you as soon as we can, and please don't feel shy to keep those coming in. We really value the interaction. These are educational presentations, and we want to make sure that you're getting as much from them as you possibly can. So that's everything from us really. I'd just like to thank you for your time, and I will thank on their behalf Steve for his technical presentation, Paul Belchamber for his assistance in setting this up. And we look forward to seeing you on future events and anywhere else that we make contact with you. Thank you again, and goodbye.